Hey, welcome back. Today we're going to continue talking about continuity in calculus. We're also going to look at a new theorem called the Intermediate Value Theorem. Super important theorem. All right, let's just do a quick review of what we discussed in the previous lesson. The definition of continuity. A function f is continuous at a point x equals c if and only if these three things are true. F of c is defined, the limit as x approaches c exists, and that the function at c and the limit as x approaches c are the same. So, with that in mind, I want you to prove whether or not the function f is continuous at x equals -2. Include a sketch of this function. So, pause the video, and then we will go over your answers. All right, let's see how you did. All right, I'm going to try and prove whether or not the function is continuous at x equals -2. So we need to, let's start with number one. That's the first one I would do. So is the function defined at -2? So I'll just find out. Well, let's see here. The function is piecewise, but it says that when x equals -2, it's -1. So it's quite explicitly defined. The value when x equals -2 is defined to be -1. So check for the first thing. All right, next I'm going to find the limit. So I'm going to do that by finding the limit as x approaches -2. Now, the limit as x approaches -2, we're not actually interested in the value when x is exactly -2. So it's fine for me to use the top branch. Because for values of x infinitely close to -2, we would still use 3x plus 7, as long as it's not exactly -2. So I'll do that. 3 times a -2 plus 7. Well, that's a -6 plus 7, which is 1. So what we can see here is that the function is defined, the limit exists, but they are not the same. So I'm going to put that in a sentence. All right. So I'll say f is not continuous at x equals -2. Why? Because f of -2 does not equal the limit as x approaches -2 of f of x. Let's graph it. So at -2, we found a function value of -1. So that would be right here. But the rest of the function, it was approaching a +1. And that's just a line with a slope of 3 that goes through 7. I think this is close enough for a sketch. And I think you can see the discontinuity. All right, let's work an example together. Let me just pull this over to my board here. My paint board, if you will. All right. We're going to find a value k so that f is continuous everywhere. All right, so I'm looking to find a value for this to make this function continuous. Well, I need to have the limit exist. I need to have the function exist. Let's start with the function existing. So f of 2. Well, when x is equal to 2, we use the top branch, and that's exactly what it is when you evaluate a function. You're saying x is exactly 2. So we're going to say 2 plus 3, that is 5. Okay. Now let's make the limit exist. Well, we need the limit to exist, and we need it to also be equal to 5. So clearly the limit on the left is 5 because we could just use direct substitution. But what I need is kx plus 6 to equal 5 as well. So I'm going to say k, when x is 2 plus 6 needs to equal 5. Right? Let me just formalize that just a little bit. The limit as x approaches 2 from the left, we can use direct substitution for and say 2 plus 3 equals 5. For the limit as x approaches 2 from the right, I can use direct substitution as well, and I get k times 2 plus 6. And in order for this to be continuous, this limit has to exist. They need to be the same value. So I need this right-hand limit to be 5, and that's where I developed that equation. So let's go ahead and solve that. 2k plus 6 equals 5. So 2k equals negative 1. I get k is equal to a negative 1/2. So now that I know that k is a negative 1/2, I found it. We know that the limit would exist, and we now know that the limit and the function would be the same. Let's sketch the graph. So our graph now is like this: x plus 3 and 1/2 x plus 6. So I'm going to be graphing up to and including x equals 2. 1, 2, 3, 4, 5. So that's going to be right here. And that's just a slope of 1, so it's just going to go like that. Then, when x is greater than 2, I'm doing 1/2 x plus 6, so it's going to pick up right where this left off, but now it's going to be a little bit less steep. But that is definitely continuous, right? Okay, so now you get to do a practice problem. This one is a little bit more fun because you have two values to find. So see how you handle that. See if you can dust off your old algebra skills. All right, pause the video and give it your best shot. Don't forget to make a sketch, and then unpause it and we'll discuss. All right, let's see how we did. Well, I need this function to be continuous everywhere. So I need to be continuous at -2. I need to be continuous at 1 as well. So in order to be continuous everywhere, we need to check these places, these x values that make us switch between branches. I mean, clearly 4 is continuous everywhere, 1 is continuous everywhere. Ax plus b is going to be just a line. It'll be continuous everywhere, but we need to make sure these branches link up. So when we're finding f of -2, it's 4. It's defined to be that way. So I need the limit, and oops, that little symbol there should not be here, should it? Because we have to be strictly greater than. All right, so now in order for this limit to exist at -2, I need the limit from the left and the right to be the same, and I need them to be equal to the function value. Clearly the limit from the left is 4, because for x values less than 2, I'll document that though. The limit as x approaches 2 from the left is clearly 4. The limit as x approaches 2 from the right, I'm sorry, -2 from the right is going to be ax plus b. So x is a -2 using direct substitution. So it'll be -2 of f. -2a plus b. I just moved the x value in front. All right, so we've got that needs to equal 4. So I would say we have one equation there. We have -2a plus b equals 4. Now let's take a look at the 1. F of 1, well, it's defined to be, when you plug in 1 here, a plus b. We need that to equal the limit as x approaches 1. Well, clearly from the left, it's a plus b, right? From the right, it's just a 1, right? So I need a plus b to equal 1. I need -2a plus b to equal 4, but I need a plus b to equal 1. All right, so all this kind of theory over here is basically just doing what I think most of you would intuitively understand, that in order to make these branches line up, ax plus b at the -2 has to equal the 4, because that's where it's coming from. And at x equals 1, ax plus b has to equal the 1. So that's where I get these two equations. Let's solve them. I'm going to subtract, so I'm just going to multiply through by a -1 here. And I'll add the two equations. B's cancel out. I'll divide by a -3. I get a equals -1. So going back to what I had originally, which was 1 is equal to a plus b, I'll say a -1 plus b. And I think that will tell me that b is a 2. So I think we found the two values. It makes our function, let's just rewrite it, for negative x plus 2 and 1. And that's for when x is less than or equal to negative 2. Negative 2 is less than x is less than or equal to 1. And x is greater than 1. All right, let's do this. So at negative 2, I'm going to be 4. So all the way up here at 4. And everywhere to the left of it is just a horizontal line. When x is greater than 1, I'm going to be at 1. So once you're past this little tick mark, you're just writing this horizontal line right here. And hopefully we picked values that connect these two. Let's plug in 2 for x here. That would be, a negative 2. That would be a negative 2 times negative 1 is a positive 2, plus 2 is 4. And we plug in a 1 for x, you get negative 1 plus 2, that's 1. So it just perfectly fills this in right there. All right, now it's time to talk about a theorem. The Intermediate Value Theorem. If each of the following are true, 1, f of x is continuous on a closed interval from a to b. 2, f of a does not equal f of b. And 3, k, some value k is between f of a and f of b. And by being between, we mean that either it's f of a, then k, then b, or reverse that. Then there exists a value c on the open interval from a to b, such that f of c equals k. So let's take a look at what that would look like graphically. So if I had, let's see, and I'll use this condition here. Okay, so f of a, here, so I'm going to call this a, I'm going to call this b, okay? Then f of a, let's make that right here. All right, so that's going to be part of my, we know that true. We know that's true. And then I'm going to put f of b up here. So that makes this up here f of b. And k is somewhere in between them, right? So I'm going to just, where do you want to put k? How about a little closer to f of b so it's not right in the middle, just for demonstration. Okay. So what we're saying, according to this theorem, is that there's got to be some place in here where the function is at k. Well, the key is this, and that's what's key, is that it's continuous. If the function's continuous, maybe it goes down a little bit, I don't know. But because it's continuous, there's no way for me to get up to here. I can't jump over the k, right? So, k, if we think of k as a horizontal height, we can't get from down here to up there without going through all of these different values in between, including at some point we must have gone through k. And that is that c value that we're talking about, that the Intermediate Value Theorem guarantees. But please don't over apply it. If it's not continuous everywhere from a to b, then you don't know. It could jump over that k, and quite often things like that happen. So be careful about over applying it. All right, speaking of applying, let's look at an example, and hopefully we apply it correctly. All right, I've got the temperature of a 60-degree Celsius cup of coffee is left on a table in a 24-degree Celsius room to cool. The temperature as a function of time the cup has been cooled can be modeled by the function c of t equals 36 times e to the negative 0.1 t plus 24. The temperature of the cup at various times t is shown in the table. Must there have been a time when the cup of coffee was 30 degrees Celsius? Well, if I'm asking for the existence of a specific x, or in this case t value, where the function equals a specific output, that's when you need to immediately think the Intermediate Value Theorem, or as it's affectionately abbreviated, the IVT. So in order to use the IVT, though, I cannot just state the answer. I have to justify each one of these steps. The IVT is quite often appears on the free response section of the AP exam so that they can judge those steps. So I must establish that it is continuous on this interval. Well, let's start with as wide an interval as I can. I could maybe zero in to the one in between 20 and 28.8 and 37, but I'll just use the 0 and 30. I think that's fine. So f of 0, oh, it's not f, I'm sorry. We're using c. C of 0. Oh, here I am. I'm jumping straight to 2. Why don't we start with 1, like I said I would do? All right. First, this function must be continuous. Is this function continuous? Well, let's talk about discontinuities. Is there ever a place where there'd be a vertical asymptote or a jump? Well, we know what the e to the x function looks like. It's a nice, smooth function that goes like this, right? And then goes out. This with a negative value, it's going to just negative x is just going to make it go down. But there's no divide by 0. There's no logarithms that have vertical asymptotes. There's no trig functions that have a denominator. So when you check those conventional bad guys that ruin your domain, that cause, when you check for dividing by 0, square rooting a negative, or logarithms of 0, those are all things that can cause you to have discontinuities. Once you've checked all those, then we can go ahead and assume that it's continuous, okay? So we're going to say that. We're going to say, and we're just going to say those words. We're going to say C is continuous, and I need it on a closed interval. So I will say that, 0 to 30. Yeah, it's continuous on negative infinity to infinity, but we're going to say a closed interval because that's what the theorem says. Next, I need to show that f of a is not equal to f of b. So C of 0 is 60, and C of 30 is 25.792. So they are not equal, and I need to establish that this value I'm looking for is in between them. Well, C of 0 is greater than, what is the value we're looking for? 30? 30, which is greater than C of 30. Okay, that's a little confusing. There's too many parentheses, too many C's, too many 30s. But hopefully that makes sense. Okay. So therefore, by the IVT, we can conclude that there exists at least one, maybe maybe more, there exists a value C such that C of C, little c, is equal to 30. Okay, I hate all the parentheses, C's and little c's, but you get the idea. We could, I'll tell you what, I don't have to say C here. I can use any letter I want. So I'm going to say a value, Q, just because I can. There we go. So I got sick of C's looking like parentheses. If I could outlaw the use of C in math, I would do it. All right. Okay, you have a practice problem to do. Please practice using the steps of the IVT. Do not skip a step. It will, 1, you can lose credit on free response. 2, you can misapply it very easily. So be careful. Make sure that it's fair to apply. All right, pause the video and give it a shot, and then we'll talk about your answer. All right, we're going to show that f of x has a 0. The first thing I'm going to do is I'm going to check this condition right here. This is a polynomial, and you can just immediately conclude that polynomials are continuous everywhere. So I'm going to say f is continuous on this closed interval. All right, cool. Now let's find what f of a is. F of 1 is equal to 1 cubed is 1, minus 2 minus 1, that is a negative 2. Let's find out what f of 2 is. F of 2 is 2 cubed is 8, 2 times 2 is 4, minus 1 is 3. So clearly f of 1 does not equal f of 2. Next, f of 1 is a negative number, so it's less than 0. And f of 2 is a positive number, so it is greater than 0. So we've got this betweenness that we need. So therefore, that's what those three symbols mean. Therefore, there exists a value c such that f of c equals 0. So I'm using just a little bit of math shorthand. I don't recommend using it unless you're absolutely certain, but they do know it on the grading. But that means therefore, that means there exists a value c. That symbol there means such that. So you can see why mathematicians do that. That's a lot less writing, isn't it? But I figure, as long as you can read that kind of stuff, then you'll be fine moving forward. Okay, so that concludes our lesson for today. I wish you luck on the assignment, and I can't wait to share more calculus with you tomorrow.